My name is Sydney Sukuta with Sukuta Technologies. I'd like to thank uh, the, the, uh, 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 the CBP, Craft Beers Professionals Organization, for inviting me to do this talk. And I'd like to thank all the sponsors. I don't remember them all, but you're doing a great thing supporting this organization because they give us an opportunity to talk to the world and share our ideas. Okay, so the title of my talk is Advancing Water and Beer Analysis Using AI. So artificial intelligence. And again, my name is Sydney Sukuta. I'm with Sukuta Technologies. So we're going to get started. So this is the outline of my talk. We'll go over an introduction, and I'll introduce the challenges, the issues that can be overcome. People take for granted as normal, that can be overcome with the employment of AI and with spectrometry, things like that. And number two, I'll talk about how the process works. First, we're going to talk about how do we extract data out of a sample. In this case, let's say a water sample or a beer sample. And then next, I'll talk about once the data is available, what does the AI do? Number three, the steps we take to acquire the data and make sense out of it. And then number four, sorry, I missed number there. Number four, we'll go ahead and do some illustrations demo. You can see how these methods are used. And then we conclude. Okay, great. So most traditional laboratory tests used to analyze properties of materials require a high degree of training and specialization in analytical lab methods, the use of a physical plant or laboratory, and a significant amount of funding or commitment to funding. And of course, all of these can be barriers if you want to do your own tests or if you're a non-expert. So if you're a non-expert and you want to do your own testing, you'll be challenged because you won't have your lack of traditional training. You can do it, maybe funding, and you just won't have a lab. So we need to find a way around it to make this universal. Okay, so often also, if you make it in that environment, the traditional testing environment, you need multiple machines to do tests. Generally, one machine per parameter of interest, and then that can be very, very expensive. So if you want to measure 5 things, you may have 5 different machines to work with. And these machines are very expensive and they require specialized training. So all those are barriers inhibiting people from doing tests they need to do. We are proposing an alternative to this, where we can use light through spectrometry to interrogate samples and get their molecular information. And after that molecular information is run through AI algorithms I'll discuss here to extract exactly what you want. Say maybe you want to know the kind of water you have, what type is it, what components in it, any contaminants, things like that, things the traditional lab will do. And this approach circumvents most of the barriers, and here you'll have one machine for all of them, all in one. And then once the algorithm does the processing, the output is going to be very simple to read. They're just plain English, nothing complicated there. Okay, so that's what we are striving to do, and hopefully, Okay, so Okay, so let's discuss spectrometry a little bit. We keep talking about spectrometer and AI. So the first thing you need to do is to shine light through the sample, and that will gather information about the sample at a molecular level. And then once that data is available, it goes to AI. But let's take a closer look at this. So here we have light, and if you ever pass light through a prism and you have a rainbow, this is what this is all about. So you pass light through a sample, it gets into a camera of the spectrometer, and you have a rainbow like this, and that has information about what's in the sample. So what we normally do is we shine the light without a sample, so we have a background, right? And then we shine the light with the sample, Now, when we compare the original light that we passed without the sample and the light we get after the sample, and how much light is transmitted through each wavelength gives us information about the sample. And then the AI takes over. So this is the rainbow created. So think of a spectrometer as something that makes rainbows. And if the light is intercepted by sample, as it goes through it, it's going to collect information about that sample. And then it's now available for us to analyze. Okay, so let's look a bit closer at the sample, in more detail. So we're going to look at a very simple illustration, but it represents what actually happens inside. So when you shine light to a sample, what you're actually doing is adding energy to the sample. And when you add energy to the sample, you see where it says NO. Electrons are what we call the ground state, So, and this is the electronic ground state. And as you go up, this is more energy, okay? And then before I say that, you need to subscribe to the notion that light is a form of energy, number one. Number two, this is an electronic energy ladder, so to speak. So energy is energy. So that's the idea here. It can come as light. In this case, the optical energy or light energy is captured by electrons in this lowest electronic energy level. And the laws of physics say that if you have too much energy, you need to go to a higher level. So once you send light in there, which has a certain energy, it will make the electrons jump by that amount of energy to the next level, maybe next or 3 or 4, whatever, it doesn't matter. And now we say that the electrons are excited. They have energy with them. They're excited. So they transport energy to a higher level, and they may lose some of the energy through, let's say, temperature change, drop, a vibration or sound, because all those are forms of energy, right? And it may go to some level. Let's call it the upper level rather. And then again, the laws of physics want electrons to reside in these low states, the ground state, kind of like the way water goes into valleys, right? That kind of thing. So what the laws of physics will do, they'll spend what they call a spontaneous lifetime. And the word spontaneous means natural lifetime. And the electrons will fall. But when they fall to different levels. So for example, an electron can fall from this N2 to N1. Another one can fall from N2 to N0 and many other levels. Now, those gaps actually represent specific colors or wavelength. So what you'll see outside is this rainbow here. See that? This rainbow here. So in this case, I'm saying you're hitting the sample. So this is the spectrum of the sample. This is in angstrom. So you can chop a 0. So this is like 400 to about 700 nanometers in the optical, in the visible spectrum. So this is the spectrum of the sample. And then this, so like I said earlier, we also pass light without the sample. So there's a comparison between this spectrum I just showed you and the spectrum without the sample. And then we get information about how much light was transmitted. And that's enough to come up with a lot of diagnostics. Okay. So this is a typical sample I get, sample data I get. So these are the samples. I took off the names of the samples because some of these companies, you may recognize them. And these are the wavelengths. So for example, for this sample, I scanned it 6 times. I got a spectrum. Another one 7 times. I got a spectrum and so on. So in this data, it's a gold mine of information. We will interrogate this data and get the information we need or the diagnostics we need. So these are the different steps. Let me wait for. Hang on. So this didn't show. Let me go back. So anyway, it's blurry a little bit. So these are the steps we take in our algorithm. So we're going to have a data exploration phase where we want to understand, what's this data doing, where is what, that kind of thing. Once we figure out, understand the data or the sample data, we'll build what we call calibration models, your AI models. And then after that, we validate the models. Basically, you look for something, you already know the answer and pass it through and see, scan it rather with light and see if you get the correct answer. And once we do that, and we have reasonable error. There's not, it won't be exactly, maybe plus or minus 5%. That's the criteria established. We go into deployment. That's our last phase here, sample deployment. So I'm going to summarize those steps. This is just an overview. So phase one, what they would call machine learning. I like to call it data exploration. We look for natural patterns in the data and exploit them to build what I call data-centric prediction models. Right? Why data-centric? Because we build models around the behavior or patterns in the sample data, as opposed to coming in with preconceived theoretical models, trying to fit the data into your models, you see. And those models, textbook models, may not match the reality we're dealing with. So what we build is data-centered models. We don't fight the data or say, okay, if this is what you are all about, we'll do something that works for you, rather than saying, according to this theory, it should be that. So you kind of build a theory customized or tailored to that particular sample, okay, or samples. So once we do that, we understand the data, we build mathematical models using the data we showed you, but we also go to a certified lab and say, for this sample, what is percent alcohol, for example? And then based on that, we look at the data and make a mathematical connection between the concentrations, the color, the pH, whatever you're looking for. So we make that mathematical connection and we build models using specific wavelengths, because some wavelengths are going to be more sensitive to pH, for example. Some wavelengths are going to be more sensitive to, let's say, color, some to bitterness, things like that. So that's how we work it, and then we build a model. And then the training of formulated prediction models are stored in a library. So some people may call this training as well. And then we store them in a library on a computer, and we invoke them when needed. But I'll explain some of the next step here. And then we go through model validation. Again, once we build the models based on what the certified lab told us, or certified samples, sometimes we get samples in a bottle, we make sure that the model is able to predict as the certified samples say. So we run certified or reference samples with known answers as a test for the developed AI models until acceptable margins of error are reached. When acceptable, then hey, it's ready for use. It's ready to deploy. So we can now use it. Okay, so I summarize the steps here. So again, we start with the calibration or model development stage. After that, we do model validation. After that, we deploy. So here are some specific steps. So you have a calibration phase. So we have sample parameters of interest identified by the user. We train in conjunction with a certified lab or certified reference. So to make sure that we correlate with the reference here. So if it's a beer is 5% alcohol at the reference site, I have to get 5% as well, and elsewhere, wherever it may go. Then after that, we kind of do the same thing, but kind of testing the models we built here. So we kind of do this. If it fails, we just keep going back until it passes. Then it goes to the next stage after it passes validation. And now we can deploy. Okay. And then they can be used. However, due to machine drift, this and that, it's always a good idea to periodically double check these models, make sure there's no drift, because we're dealing with machines here. Okay. So that's what we do. So these are ready for use when they're ready for use. Next, let's delve a little bit more into the deployment of these models. So the way I work is we have our users here. So probe is like a user, probe 1, 2, 3, and wireless communication. So a user can communicate with a server, okay? With a server where the algorithm resides. So you have, like, let's say you have 3 or 4 users here. So you have each user's machine is able to go to the cloud and actually extract the latest formula we have, and on their machine, Every time you turn on the machine, it can go to the server and make sure there's no updates. That's the kind of thing we're talking about. Okay, so let me read here. So models could be deployed into a server where they could be accessible to multiple users. So it could be somebody in the brewery or process. It could be somebody in the field, offsite. It could be somebody in the lab, even a bar, if they want to check their drinks, to make sure, that kind of thing. So there's that communication, and in the cloud server, that's where the formulas reside. Again, the whole idea is that when you turn it on, in case there's an upgrade, and also login credentials, things like that. Okay, so this is fairly accessible, far beyond one site. So here also, let's look at what happens inside our prediction models. So as a user, the first thing you want to do is to identify who you are, and then what do you want to measure, okay? And then you can have an option to have data stored if you want to look at trends over, maybe over 6 months, what's changing here. Or you can just go down here, real-time analysis, where again, we probe the sample using the spectrometer, as I explained already. And it is processed, and you predict. Okay, you declare that you want to predict, and then it goes back here. It will classify the sample first, and I'll show you. It's gonna classify the sample. If that's all you want, you're done. Next, you have the option to quantify. Like if you want numbers, like pH 7, ABV, let's say whatever, a percentage. So if you want to predict here, so here in general, so you have an option to go prediction if you want historical, or prediction if you want real time. Either way, of course, yeah. And you get your answers, done. Okay. So as sign up, the first thing I showed you earlier, just your name, contact information, and as you do that, you pick a plan. For example, basically what analytes do you want to check? So for water, excuse me, you could be zinc, sulfate, chloride, bicarbonate, magnesium, whatever water chemistry you want for your brew. So we can predict that, how much is in it? Is the zinc even there? How much of it's there? Is the sulfate even there? And so on and so on. And then on the water side, and while I'm at it, the reason why I got interested in water, first it was beer. Then I said, wait a minute. If the water chemistry is not exactly what you want, you're not going to get the beer you want. So it's very important that the water chemistry is profiled, number one. Number two, once you identify the water chemistry you want, to make sure it's consistent. And this AI spectrometry will do that. It will check and say, this is not the water you used last week. So you can have your water chemistry guys, and girls, whatever, kind of do that, or wherever you buy it, All right, then you go to your beer. So, so starting from the beginning of the process to the end. For example, starting with wort, fermentation, filtration, all the processes to until the product is ready. So like yeast counts and fermentation, fan, sugar at any level, of course, ABV, bitterness, color, and so on. Those things can be predicted. So there's really no limit to what you can predict the way we have it. So as you want to predict more stuff, you don't have to buy more instrumentation. This is a one instrument for all, with this AI option of AI and spectrometry. So typical classifications, for example, you may want to know, is this water RO or reverse osmosis? Is it purified water? Is it ultra purified water? You may want to know that. I do understand that people in the brewery space will be brewing, they're interested in RO water. And then the next question would be, is this RO water the same quality as the one we used before? Because you want consistency, right, in your product. So this can be done very easily, and I'll show you some examples. So those are typical classification solutions. Also, typical quantifications will be, for example, what is the pH? and how much of each of the constituents, is in it, like how much zinc is in there, and the machine will tell you, and you can decide it's whether it's enough or too much, whatever your situation is. So all those analyses I described, they can be quantified and more. I just put a few here, and again, all tests are on one AI powered machine. You don't have to buy different machines for different things. It's one in all. Okay, so basically it's signing. You check off what you want. Maybe you don't want all of these. Okay. So that was the water side. Let's go to the beer. For example, verify the authenticity of input ingredient, and the biggest input ingredient in beer is water, as we discussed already. That if your water is not exactly there, it may not give you the best. You may want to check on the yeast. Is this the correct yeast? The yeast have different species, right? Is it the correct ones? Or maybe the yeast degrading? What is the vitality or viability of the yeast, the grains, the quality? As they're coming in, you may want to screen them to make sure it's not just the water. If the hops are not good or the grains, that's going to mess up your brewing, right? Or your brew. Things like that. So these things can be verified as they're coming in. Then on the quantification side, at every stage of the process, as I mentioned earlier, we can quantify sugar. They call it PE or PEA, sugar before and after fermentation, FAN, yeast vitality, yeast count, how much sugar, alcohol, bitterness, color, pH, and so on. And again, it's sign up for, let's say you decide to do this. You can tell your machine, make sure you do this, for me. At least this week, next week, I want something else. You have that flexibility as well. Okay, so we're going to do some illustrations. How does this work? So, I may not be able to cover all of them. I'll just give you an idea. And then if you have any questions for me, my email is down there. AI_solutions@sukutatechnologies.com, or I prefer that one. The other one is Sydney@brewmetrics.com. Too much spam on that one. Okay, so let's do some demos. Okay, so here, water. Okay, so there's what they call ASTM water types, or deionized water types. There's type 1, 2, 3, and 4. So I did run 1, 2 from water from one company, and then I went to 2 other companies. I ran their type 3, Okay, and then I also ran distilled water. So what is this? This is called hierarchical clustering. And a simple way to think of it is a similarity test. It's a similarity test. So here we see that if you look at this closely, unfortunately, it may not be that clear, but I have another diagram I want to show you. Type 1 and type 2, the data comes in and we do a calculation here. And it finds that type 1 and type 2 ASTM water are very similar compared to type, here I have type 2 and distilled water, that kind of thing. So this is like a one-dimensional view. It's not very clear, but I just want to throw something else in here. So I'm talking about water. Another thing you can use this for is to look for similarity between your products or even the competitors. Maybe there's a leading product, we can run something like this and say this lead, kind of like your positioning of your product in 2 ways. One of them is compositional, how do they compare? Another thing is to do those sensory panels, and we can run stuff like that, and we can tell you, how it compares, So ideally, let's say this is the leading product, you want yours next to it, right? But if they totally goes the other way, maybe you have some work to do. But anyway, back to water, we look at these similarities. Not the best, but the better one is this one, where we have type 1 here, type 2 here, we have type 3 here, and the distilled water here. I couldn't get type 4. Somehow, because the purity tanks as you go to the left. So, anyway, so this is where the RO water is here. And actually, I have two companies' water here. The one here is one company, the ones down here is one company. So even within the RO, which I know brewers like to use, there's a bit of discrepancy here and there, but more or less they match. These companies were pretty much a match. So that kind of thing. So you can then run the water you have to make sure it's where is here if you want RO water. Some people may want purified water. I don't know, but I understand brewers like to use this RO water or type 3 ASTM water. Okay. And okay, so that's, I think this is more clear than the other one. So you can, so this is the knowledge we acquire during machine learning or data exploration, and then we code it and put it in the server, and then we can have automatic classifications. So this is what I showed you earlier, but I'm trying to show that when we analyze this, these are like an Earth, longitudinal modes, So you find that we do not expect each, like this pair of longitudinal modes, parallel lines, the sandwich or in between there's ultra pure, this is type 2 water or purified water, RO water, and so on. So sometimes if water is of the same type, but there's intra-group differences, they may splatter down this way. But two distinct groups should not occupy the same longitudinal modes. Okay, so there's a little bit of detail there. So those are the kind of things we check for to make sure that there's the distinctions between these waters. Actually, I had another company that was selling water at type 1 and 2, and I didn't want to use it because their samples were overflowing in here. So that would create a lot of ambiguity because they mix it. In fact, on their bottle, they say type 1 and 2. And when I put it here, it does exactly that. So anyway, so let's get the water straightened out. Is this the water we want? And then we can start to brew. And then also, in addition to this is the water we want, we can do also compositional analysis. What's really in that water? Okay, so your zinc, sulfates, and all that. But this will be the first line of screening before you get details. Okay, so I'm gonna jump onto beer. So these are some of the illustrations from water analysis, where I think the first big thing is this the right water for me? Then the next level is what's in it, compositionally. Okay, so those are some of the examples we can do with using AI. And then beer. Since we pass light through the beer, let's say this beer here, the pale straw beer is 5% alcohol. And this beer here, like Guinness, is 5% alcohol. When you pass light through these beers, they're going to have different transmission values. And so that can mess up your algorithm. So what we found out, and I'll show you in a few minutes here, is that let's put these beers in buckets that are more similar. So because more or less, like if they're in the same band, they'll have more or less the same transmission values, the light. So the analyzer sorts the beer into 3 color bands, namely color band 1, 2, and 3. For reasons I told you, that we depend on transmission values, as I told you at the beginning. How much percent light went through? Again, if these two beers have the same, like this one, the extreme ones, have 5% alcohol, 5% alcohol, the transmissions are going to be very different. This one is going to transmit more, and this one less. And since we use transmission values, the answer is going to be wrong. So by doing this, we find that the answer is no problem. So the first thing we do is categorize or classify our beers by color, unlike water, which is, so that's the first thing we do. Then after that, we focus on each color band, so we'll have a different algorithm. Let's say percent alcohol for color band 1, a different algorithm for color band or formula for color band 2 and 3, and so on and so on. Okay, so what we're going to show next is how this is applied, and we're going to focus on color band 1 for our example. So when we run the samples, the first thing we do is determine the color band, as I explained already. So it's going to be either of these. So the ones I'm going to show you are in this category, the more pale, kind of, yellow, orange looking. Okay, so you're going to see, and it will say CLR1, as you see here. that means color 1, then we check. So what I'm going to do here, I'm going to show an example where we want to check if a beer is non-alcoholic or it is alcohol in it, So that's what I'm going to show you. But I want you to understand when you see the GUI. Okay, so I have here a video that explains that. In this video, we demonstrate that an AI smart spectrometer can be used to differentiate between non-alcoholic and alcoholic beverages without the need for chemicals or traditional setups. So let's take a look. Oh, hold on. 1 second. Okay, I think my hyperlinks are not working here. Let me go back again. Okay, maybe let me wait for a few minutes. Okay, I don't think I'm able to play this video. Let's see. Okay, anyway, that's okay. We'll visit this later. All right, so next, so I can explain what we do in this video. So what we're doing here is we have alcoholic and non-alcoholic beverages, and we run them, and the machine, if you can see here, it says color 1. Like I said, I'll do color band 1, and then it will say is alcoholic or non-alcoholic. Alcoholic, or I did about 2 or 3 of those. So that's one way to do it. Now, that's one application. As I told you earlier, you can use this technology to screen. For example, if somebody's giving you water or whatever, you can use this. Where I say non-alcoholic, it will tell you, for example, this is not the hops you ordered, or you agreed to, that kind of thing. So unfortunately, I can't play these videos because the link, when I click on it, it jumps to. Okay, that's okay. So then, otherwise, so I'm saying, for example, typical strategic tasks other than your regular analytical chemistry. So, for example, how well does a beer compare with the competitors? Leading brand, you can do that. As I mentioned earlier, by composition, which is fine, but also by sensory, because that's what the customer sees. So like color, taste, things like that. You can do a sensory panel, and using that data, we can do those similarity analysis I just showed you earlier to see how well. So I just call that strategic, and things like that, because it's not really typical analytical chemistry. So let's see what's next here. I don't think this is going to work as well, but what I'll read here. So the video showcase wine can be authenticated using AI smart spectrometer without chemical treatment. The technology is demonstrated using different wine samples for testing and analysis. So again, what I have here, this company, I had this beer, or this wine, I'm sorry. I know this is a beer forum, but it's close enough, I thought. So it's Sutter Home Wines. And then we went through the process, and then we ran to, let's say the Merlot or Chardonnay. The machine will say yes or no, and then I'll try other brands. The machine will reject it. No. It's not, that kind of thing. So in a broader sense, I'm reading here now, this technology can be used to validate the authenticity of incoming materials, such as raw materials coming in, and then finished products that are coming to you, either way, in addition to your regular analytical tests, So unfortunately, I can't play this video. I will send it to the organizers. Maybe they can try to fit them in so you can see a real life a demo here. Or maybe we can try later. Okay, great. And then this is the updated version of the machine. Basically, I call it lab the size of a food tray, basically. You can just hold it in your hand like this. So where this is the sample port with light coming in, hitting the sample and going back to the camera. And then the data goes to the computer, analyze, and you get your results. And then you can read some of them on the screen. Some of them are stored on your hard drive. All of them, rather, will be stored on the hard drive and also on the cloud server. So this is it. It's very simple. It's portable setup, And as you can see, all you have to do is click. Once you run a sample here, you just hit, for example, here it says next step, next sample, post data, done. You put another sample, next step, and so on. All these, just run through these, next sample, next step, post data, done. When you put post data, the answers show up here. No chemistry needed. You don't have to know anything about chemistry or anything like that. And once you're done, you go back, put another sample, and you run it again. Now, what I also want to mention is that this setup, our team can also integrate it in your process or brewery. So where it's automated. All right. So we're going to conclude. So we've shown that barriers to water and beer analysis can be overcome through the use of AI spectrometers. So you don't need a brick and mortar laboratory to do this. You can do it off your office desk, lab, field. You can even go to process and do it manually or integrate this system in the process. Again, only one analyzer required, one for all. Okay. And then moreover, the trace size spectrometer can be brought to the sample. Usually when you have a sample, you have to go to the lab. Now you can take the lab to the the lab, which is the spectrometer, to the sample, that kind of thing. And then there's no set limit. We're not going to say, oh, you can only do 5. No, you can do 5, 50, 100, whatever. There's no limit. It's up to your imagination and the limit of your computer. So we think this is the lab of the future. Okay, here are our websites, spectrometrics.com. That's where we make the spectrometer. And I have a dedicated site for water purity. And this is our general website. Thank you for your time. I appreciate it. Thank you so much, Craft Brewers Professionals Association. I appreciate what you did. Thank you so much. Thank you.
Thanks for watching. If you enjoyed this session, we'd love to see you in real life. We host in-person workshops across the country for craft beer professionals just like you that are held in some of the most exciting beer destinations around. These immersive events are designed to help you grow and connect with others. You'll meet peers from across the country and leave with actionable strategies for success. Connection has never been more important, and you can learn more at cbpconnects.com. Cheers. See you there.